Dear viewers, in the last lecture we have discussed about the various aspects of process scheduling and CPU scheduling. In this lecture we will discuss the concepts of process synchronization. We will discuss about interactive and cooperative processes, critical section problem and semaphores. First, we are going to start with interactive processes. Interactive processes allow users to enter data or commands during the execution of the process. The user gives instructions to the operating system or to a process directly and receives an immediate response. An interactive process provides online communication between the user and the system. Most popular programs such as word processor and spreadsheets are interactive processes. Also, the email process running on your system is a good example of interactive process. During the execution of email process, after short execution, email process asks for input data like login and password. Email process returns the inbox and wait for the user to click on any mail or whatever. In this process, there is extensive user interaction with the email process. Time sharing operating systems are primarily used to handle interactive processes. Second, we have cooperating processes. The concurrently running multiple processes in multi-programming may be independent or cooperating processes. A process is independent if it is not affected by and cannot affect other processes. Independent processes do not share any data with any other process. On the other hand, if a process shares its data with other processes or the process is affected by other processes due to sharing of data is called cooperating process. There are many reasons for having cooperative processes. First is information sharing. Several processes may require accessing of same piece of information. Operating system must provide an environment to allow to concurrent access of a resource in sharing method. Second is computational speed up. To increase the computation speed of a process, we can divide the process into subtasks, each of which will be executing in parallel with the other. These subtasks will be cooperating processes. Modularity. It is difficult and less efficient to make a big process undergoing all useful activities. Instead, the system may be constructed in a modular fashion, dividing the system into separate processes. These separate processes will have to cooperate with each other to complete some particular task. Last is convenience. User may have multiple tasks to perform at one time, making the system convenient to use. To illustrate the concept of cooperating processes, producer-consumer problem is best example. A producer produces information that is consumed by the consumers. For example, print program produces data that are to be consumed by printer to print. Synchronization between producer and consumer is required so that the consumer does not try to consume an item that has not yet been produced. We need buffer of items that can be filled by producer and emptied by consumer. Producer-consumer problem can be implemented using unbounded buffer or bounded buffer. Unbounded buffer places no practical limit on the size of the buffer. Consumer may wait, producer never waits. Bounded buffer assumes that there is a fixed buffer size. Consumer wait for new item, producer waits if buffer is full. we have shown working of bounded buffer producer consumer problem in this figure. Here buffer has been implemented as circular queue. Producer produces item and puts in circular queue at in pointer, and consumer consumes item from out pointer of this circular queue. Initially in and out pointers will be null. The various conditions and working of producer process and consumer process have been shown in this figure. The cooperating processes may communicate with each other by sharing common data structures between them, as we have already discussed in producer consumer paradigm. Another method of communication between cooperating processes is using inter-process communication facility called IPC. Inter-process communication is the method of exchanging information between cooperating processes. IPC provides mechanism to allow processes to communicate and to synchronize their actions without sharing the same address space. During inter-process communication, the process sending the information is called producer and the process receiving the information is called consumer. Generally, in many applications, roles of producers and consumers are fixed and communication is repeated many times. For example, the printer is always consumer and keyboard and mouse etc. are always producers. But in some other cases, any process can play the role of consumer or producer depending upon its activity. For example, email program running on your computer is consumer when it asks for login and password, but it behaves like producer when it displays the mailbox. There are two methods of communication between processes. First is direct communication or message passing method. In this method of communication between two processes, first a link is established between the processes. It can be a unidirectional or bidirectional link. Then two primitives send and receive are used for communicating data through kernel. Send primitive is used by producer and receive primitive is used by consumer. In this figure, process A is sender and process B is receiver. Using direct communication, process A sends message M to kernel indicating the address of receiver. Kernel sends the message M to receiver process B. Therefore, all communication between cooperating processes takes place through kernel as shown in figure. Second method of communication is indirect communication or using shared memory. In this method of communication between two processes, processes share a common area of memory for communication. First, a link is established between two processes by sharing a common memory area. After that, producer process writes the information to be communicated in shared memory area. The consumer process reads the information from that shared memory area. Processes themselves manage the shared area and do not require kernel for communication. In this figure, again process A is sender and process B is receiver. Using indirect communication, process A writes message to shared area of memory. Receiver process B can read the message from shared memory area. Hence, using this method, cooperating processes share some part of their address space known as common memory area as shown in figure. All communication takes place through this common area. Next, we are going to discuss process synchronization. Other than just passing information between them, cooperating processes may share some resources and concurrently use them. As concurrent processes need to compete for shared resources, it is very much required to coordinate their activities or shared resources to avoid any inconsistencies. The method to deal with systematic sharing of resources between concurrent processes is called process synchronization. Synchronization involves the orderly sharing of system resources by processes. To illustrate, one can see this road intersection diagram. Here, road intersection acts as a system resource that is shared by two processes, the car process and the bus process. If only one process is active, then no resource conflict exists. If both the processes are active and using independent resources, there is no problem. But what happens when both processes are active and they both arrive at the road intersection simultaneously? In this case, the shared resource becomes a problem. They cannot both use the resource at the same time or collision will occur. Similarly, processes sharing resources on a computer must be properly managed in order to avoid collisions. This concept can also be explained with the help of a shared printer. Consider a machine with a single printer running a time sharing operating system. Let we have two cooperating processes requiring printer concurrently. One process is to write A, B, C in small letters, another writes C, B, A in capital letters. If both processes were given simultaneous access to the printer, the results would be worthless to both. One can see in figure that it may produce correct results, but the possibility of producing incorrect results cannot be ignored. This example is perfect example of race condition. Race condition is situation where several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which access takes place. Next, we are going to discuss critical section problem. When shared resources are modified at the same time by multiple processes, data errors or inconsistencies may occur. Sections of a process which may be changing common variables, updating a shared table, writing a shared file, etc., are called critical sections of the process. One process may have many critical sections in it. It is highly desirable that when one process is executing its critical section, no other process is to be allowed to execute in its critical section. Concurrent execution of critical sections of two cooperating processes may result in inconsistencies or a disaster. There are few algorithms to solve critical section problem. A solution to critical section problem must satisfy the following three requirements. First is mutual exclusion. If process Pi is executing in its critical section, then no other process can be executing in its critical section. Second is progress. If no process is executing in its critical section and there exists some processes that wish to enter their critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely, and this selection will be done by the processes which are not running in their remainder section. Third is bounded waiting. No process should have to wait forever to enter its critical section. That means a bound must exist on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. The code executed by a process can be grouped into various sections. Some of these sections require access to shared resources, and during execution of their sections, other processes are restricted to use shared resources. The section of the code which uses shared resources exclusively is called critical section. The journal structure of a process using critical section is shown in this figure. Entry section of the process contains code for taking permission to enter in its critical section and to use shared resource in exclusive manner. If process is eligible to enter in critical section, it is allowed to do so, otherwise it waits. Critical section contains all the instructions or code to access the shared data. When one process access shared data in critical section, no other process is allowed to enter its critical section. Exit section is the section of the code executed by process after using its critical section. Exit section contains code to inform other processes that it has finished its critical section. Remainder section contain all other instructions of process. A process in remainder section also implies that it does not need to enter in its critical section. Next topic is semaphores. Mutual exclusion or the problem of critical section can be solved using a synchronization tool called a semaphores. A semaphore is an integer variable that has some initial value and is accessed only through two standard atomic operations, wait and signal. Wait operation, also known as down operation, decrements the value of semaphores. Since the value of semaphores cannot be negative, the process blocks if the value is 0. Similarly, signal operation, also known as up operation, increments the value of semaphores. If there are any processes waiting to perform a wait operation, then they are unblocked. The syntax of wait and signal has been shown in this figure. Here we have used semaphores S. Initially the value of S is 1. Now if a process A wants to enter in its critical section, it will have to execute wait operation. Since the value of S is 1 and condition becomes false, it makes the process A to enter in its critical section and the value of S is set to 0. Now in the meantime, if any other process wants to enter in its critical section, then that process executes wait operation. Every time condition in wait operation becomes true and processes are looped in no operation loop. When processes exits the critical section, it executes signal. If there are waiting processes, one of them will be released and this released process enters the critical section. Note that the S is still 0, which means all subsequent processes that try to execute wait are blocked. On the other hand, if there are no waiting processes, the execution of signal causes the value of S to be incremented by 1, making its current value to 1. In this case, the next process that executes wait can enter the critical section. Therefore, signal is similar to unlock. Initializing a semaphores to 1 creates a mutual exclusion semaphores. Initializing a semaphores to 0 creates a signaling semaphores. Initializing a semaphores to other values can be used for resource allocation and synchronization. The operations of wait or signal are atomic. This means once the activities of wait start, they will continue to the end without any interruption. More precisely, even though there are many steps to carry out wait and signal, these steps are considered as a single non-interruptible instruction. Similarly, the same applies to signal. Moreover, if more than one processes try to execute wait or signal, only one of them will succeed. The main problem with implementing semaphores is busy waiting. Busy waiting wastes CPU time. To overcome the problem of busy waiting, blocking has been used. With blocking, a process that fails to acquire the semaphores does not loop continuously. Instead, it is blocked and another process is scheduled. A process that is blocked waiting on a semaphores should be restarted when some other process executes a signal operation. The process is restarted by wake up operation, which changes the process from waiting state to ready state. Blocking is more efficient since it does not waste CPU cycles and allows other processes to make progress. Finally, we have conclusions. Interactive processes are the processes requiring user intervention to progress their execution. The cooperating processes are extremely useful, but it requires special attention to make a secure communication between cooperating processes. Also, the resources shared by cooperating processes are synchronized in a definite order to maintain consistency. Critical sections of processes are to be handled very carefully. A semaphores is one of the methods to solve the problem of critical sections. Thanks.